Hello and welcome to this presentation and demonstration of my final year Computer Networks and Cybersecurity project. This is a flow-based botnet intrusion detection system which utilizes bio-optimized machine learning models to detect botnet behavior on a network. Bots are simply put just software applications that are designed to run automated tasks over the internet. An example of a good bot would be a web crawler, which is used in search engines. Botnets are a collection of these bots at a scale, which are coordinated by a bot master, which via a command and control mechanism. Therefore, attacks can be coordinated with the cumulative bandwidth and processing power of all of the bots, which means they are an extremely dynamic and versatile cyber threat. They can be used for DDoS attacks, spamming attacks, identity theft, or even crypto mining, as some examples. They exhibit certain characteristics as well, in terms of their architectures, communication protocols, and propagation mechanisms. Generally, botnet detection is conducted using signature-based detection. This is where a payload signature or fingerprint of a known botnet's network communications is known and utilized in specific rule sets that are used in a detection system. However, such detection methods result in high false positive rates due to the large rule sets used and generalization of some of the rules. However, botnets utilize many network-based detection evasion mechanisms. These can take place in the payloads, in the ports, and in the protocols. Some examples of the payload-based detection evasion mechanisms, which directly obfuscate the payload that is used in the network communications. Some examples of the payload-based detection evasion mechanisms include polymorphism, blended attacks, fragmentation, padding, and encryption. And then port and protocol-based evasion mechanisms can include the utilization of common port protocols for firewall traversal, or the utilization of port flux, which changes the port numbers dynamically in order to find ports that aren't blacklisted and allow firewalls to be traversed, and also evade specific rules that are looking to match against port numbers. This raises the research question of how can we detect botnets where they don't have fingerprints, where they're utilizing detection evasion methods to obfuscate their payloads. Features can be extracted from aggregated packets in a conversation between two nodes, which forms a network flow. No application layer payload data is included in these flows, only the extracted features from those flows. Therefore, machine learning can be used with botnet datasets that are in a network flow format in order to create models that can detect specific botnet behaviors. Multiple classification methods are evaluated in this research and then optimized via a genetic algorithm. Here are some of the results from the classifier evaluation with default hyperparameters, and we can see that the highest performing classifier is the random forest classifier. The F1 score is the harmonic mean between the precision and recall metrics, which is used to represent the performance of a classifier. A genetic algorithm can be applied to hyperparameter optimization as a means of more efficiently finding a fitter set of hyperparameters for each dataset. It utilizes a gene pool search space to allow high hyperparameter resolution for integer and float-based hyperparameters. This convergence towards fitter hyperparameter sets allow the averaged F1 scores can be improved on a per dataset basis. When this is conducted over all of the classifiers, we can see that the largest improvements come from the weakest performing classifiers, such as the neural network 2 at the bottom there, which goes from 0.62 to 0.82, with an improvement of 0.2. However, the highest performing classifier, even after hyperparameter optimization, remains as the random forest classifier, with an average score of 0.977. If we break down the random forest classifier's results on a per dataset basis, we can see down the left hand side the 15 datasets that are used, with sizes ranging from around 20 megabytes to over a gigabyte, we can see that the F1 scores improve from the default hyperparameters to the genetically algorithm optimized hyperparameters. As you can see, the fittest chromosomes or hyperparameter sets that the genetic algorithm produces are all different on a dataset by dataset basis. This helps improve the F1 score and ultimately the accuracy as well. The accuracy is shown on the right hand side in red, and the average at the bottom there of 0.998. The product is designed to utilize the models to facilitate detection of network flows received on the machine. It features scalable model sets, so more models can be included in the detection system when they are made for new different types of botnets. And also the sniffer supports multiple input types, the default being that raw live network sniffing, where it takes traffic from a port mirrored port on a switch and processes it into those network flows, which then gets fed into the detector to allow the predictions to be made. It also supports raw packet capture files and pre-processed network flow text files in the sniffer, which gets dynamically configured if the command line argument is present and pointing to one of these types of files. It also features a dashboard style graphical user interface made using the Electron framework, so that's with the Node.js backend and a JavaScript frontend, to allow the data to be displayed in various formats. It also supports file logging for the alerts and label network flows in two separate files, and also more updates are being worked on currently, such as the inclusion of the desktop notification alerts in the current version. So this brings us to the demonstration of the product. We can see in the top left hand corner we've got a virtual network running, which is similar to the diagram shown before. In the bottom left hand side we've got a network traffic machine, which is the bottom left hand virtual machine running here. On the bottom right we've got a malicious traffic machine, which is the bottom right hand machine that is running, and the top right is the botnet detector intrusion detection system, which is running the detector and user interface as well. To show the operation of the product, I will start the detector with no user interface initially, and you can see it's loading all 13 models successfully. It's opening both files for login operations, and it's also starting the sniffer, which is configured in a network sniffer and flow processor mode. So it's taking the raw packets from the network that it receives on that port mirror port, processing them into network flows, and then feeding that into the detector itself, which is then doing the predictions using the models that are loaded. I will now inject some legitimate traffic from the normal traffic machine on the bottom left hand side here, which is now running, and that this machine is 192.168.050, and then let's go into the edge machine here, which is a gateway device, gateway router, and you can see these flows are being received here live. So you can see the source port of 192.168.050, sorry, the source IP, and the destination IP 192.168.0.1. So we can see these flows being collected in the system by the sniffer, and then the detector is making a prediction as to what these flows should be classified as. So all the models are reporting that these flows are normal, and we are getting no alerts here. I will now run the program without any command line arguments, which starts the graphical user interface, but also runs the backend. So the backend detector runs with a WebSocket client that connects to the user interface's WebSocket server. We've got a home page here which shows the number of total flows and the number of bot flows that are counted. We've also got a detected bots table here, so any bots that are detected, it counts the amount of flows that that unique bot IP exhibits. We've got an alerts page which shows a more readable format for the alerts that are received. The activity graph shows the network flow activity over time, and the red activity shows that the predictions that are made are bot predictions. The blue shows just the total number of received flows. And then we've got a network flow log page which just shows the label network flows in a more readable format. For this example, with the malicious traffic machine on the bottom right, I can TCP replay some malicious traffic from the Menti bot, which is in a PCAP format, into the network, which should be received and then processed by the botnet detector. So now we can see that the bot flows are being counted for this specific bot. The alerts are being generated on the alerts page. And the activity graph as well should show this bot activity over time as it's being collected by the detector. So this is showing the activity with malicious traffic being injected onto that network, and we can see that the bot flows are being incremented as such when the alerts are being raised. And you can also see the activity graph as well, showing that bot behavior as well. There we go. We can set that x-axis display limit to 50, so we can see more data samples being displayed. More developments are coming with this. Like I say, the user interface is extremely extensible, so it can be customized and new features can be added quite quickly to it. New pages or new ways of displaying the data, whatever can be more suitable for it. So yeah, thank you for watching.